Bismillahirrahmanirrahim. So we have been studying the filter design, starting from the analog filter design and the digital filter design. In the last section, in chapter number 10, we talk about the step-by-step design of digital IAR filter. We have done it in the last session. Today we'll talk about two chapters. Chapter number 11 is the structures for realizing digital IAR filter. So how to implement the IAR filter. In the chapter number 10, we talk about the design. So we have already designed our IAR filter. Now how to implement it in the hardware. So this whole chapter is your homework. So just go through this. I believe that this is very straightforward, how to build the structure practically, because we have done the filter design ourselves, the procedure, and now the structure in the implementation of the structure from the hardware point of view, or you can say from the logic point of view. There are some topologies direct from one structure, direct from two structure, that is already been studied in our BSc. Based on that, there are some other topology by which we can save the memory locations. We can reorganize our system for implementing the filter in an efficient way. So this is direct from two structure. So if you follow the process, I believe this is not very difficult to understand. Still, if you have any problem after screen through the whole chapter, we can discuss over that. So this is all about chapter number 11. So where it is discussed about the serial parallel construction of the system. So how they will be represented. I believe that this is very easy and straightforward. Now moving to the chapter number 12. Chapter number 12. This is step-by-step design of digital FIR filter. So we have already designed IAR filter. Now it is the time for the FIR filter. The concept to design the FIR filter is very easy in a sense and straightforward. However, there are different type of implementation. So we need to go one by one for that implementation processes. Okay. So at the very beginning, it is mentioned that this is the equation for the for a FIR filter. So this is a FIR filter of general type where we have our output. So final output, it depends on the input value and the delayed version of the input value, and the summation of the input values will give or produce the output. The fundamental difference between the FIR and IAR system is that in case of FIR system, we don't have any feedback from the output to the input or anywhere. So we don't have this for the FIR filter. For the IAR filter, there are some feedback, and we are also introducing some delay. There might be one delay, two delay, three delay, any sort of delay. So FIR filter only need your input and the delayed version of the inputs, and that is all we need. And this is for the causal system. If there is a non-causal system or anti-causal system, then we might also have xn plus 1 and x plus 2. That sort of term may also introduced with this delayed term, and that is a non-causal or anti-causal system. However, for practical implementation, always we look for the causal system. Causal system means you need the present input and the past inputs, and that shows the causal system. So the FIR system is not a recursive system. So there is no feedback. That means there is no recursion in this kind of system. So in the introduction part, they talk about the FIR system. I believe that we already talked about FIR system for different occasions. The steps for implementing the FIR system, we can go into detail by the example. At the very beginning, we can just mention that for the pass band of FIR filter, we determined the system response, the magnitude response of the pass band should be equals to 1. From there, we can justify this y omega is equals to x omega from the magnitude point of view. That means input is equals to output. In case of FIR system, it is possible or relatively possible, but in case of IIR system, this value is, most of the cases, this value is less than 1. Maximum equals to 1, but it is less than equals to 1. In case of FIR filter, we can make it the magnitude is equals to 1. From this analogy, we can say that the magnitude of the input is equals to the magnitude of the output for the pass band. And in this case, we just are concentrating on the magnitude portion, not the phase angle. If we also consider the phase angle, we can consider this equation, as we can know that this is the magnitude part m, and this is the phase part omega n. So this omega n can be represented as theta. So theta is equals to minus omega n. So that is the phase angle. And as we can see that this is a linear phase. This is another important point for the FIR system is our phase is linear. Phase is linear for FIR system. So the phase angle for the FIR system is linear. In case of IIR system, this is for the IIR system, always we have non-linear phase. We have given this example probably before. Today we can also introduce this linearity and non-linearity with some example as well. So this is a very important phenomena that in case of FIR system, the phase is linear. That means the delay, the phase delay, or you can say the group delay. What is group delay? Do you know what is a group delay? Any of you?
No, sir.
Okay. So then we need to give some extra lecture on that. So what is group delay? Let's say if you have a number of frequency in your input. So let's have, you have xn. What is the frequency band? Let's say the frequency band is 0 to some value pi by 6. So that is the band of the frequency in the normalized frequency. Okay, so this is a normalized frequency that is from 0 to pi by 4, or you can say from 0 to 2 kilohertz. Okay, let's say kilohertz. So that is the input frequency. Now for each and every frequency component, there might have some delay, and when it reaches to the output as yn, when it represent the yn. So how many frequency component you have in xn? You have actually 2k frequency component. You have 0 and in between. Okay, so you have a lot of frequency component inside xn, infinite number of frequency component. Now all the frequency component will not reach at the same time to produce the yn. So let's say for 0 hertz, it makes a delay n samples. For 2 kilohertz, it makes a delay of samples like n plus 20. Let's say n plus 20, for example. If it is so, then this is a non-linear system. Non-linear system means each and every frequency makes a different sort of delay. So then to construct this yn, how long you need to wait for 2 kilohertz or 1.5 kilohertz or 1 kilohertz is a matter of fact. So if I just draw it here, the phase, let's say this is the phase. If the phase delay is like this, with respect to, this is pi by 6, the frequency. So at this direction we have omega. So if the phase delay, you'll see that the phase delay is linearly decaying. Let's say the phase delay is like this, minus omega n. So here the n is a constant, minus omega, only the minus omega. So when omega is increasing, that is decreasing. With the value of omega, it is decreasing. So at this moment, what would be the value? You know this because this is a linear. And then if I try to find the group delay, since this is a linear, what is the group delay? Group delay is nothing but minus, there is a minus, and then again d theta. This is your theta. D theta divided by d omega. What is that value? That is nothing but capital N. So there is a n, let's say n is equals to 100. So 100 sample delay for each and every frequency component. So this phase response is for FIR filter. So this is the phase response for the FIR filter. In case of FIR filter, the phase response is linear. That means the group delay, if I talk about the group delay means minus d phi by dt. So this is known as tau theta. So here this is tau theta. What is the group delay? That is a constant value n. Constant value n for what? For all the frequency components from 0 to pi by 6. From 0 to pi by 6, for all the value, you have the same amount of delay. So that means how long you need to wait to reconstruct your omega n? You need to wait for n samples for all the frequency, and you can reconstruct your signal back. But if you have non-linear, now there is an example of non-linear phase response. So this is theta or phi, and the non-linearity like this. Maybe this is a non-linear for 0 to pi by 6. Now since this is a non-linear, of course the tau theta should also be non-linear. So it will be like this, any sort of, let's say there's a minus, so let's say like this. Let's say like this. So now this is difficult to understand which samples or which frequency component should, for that component, how long you need to wait. So there is a problem, and that problems actually occurs in case of which kind of filter?
FIR filter.
Or IIR filter.
Oh, IIR.
Yeah. This is a non-linear filter. So that's why there is a problem. Okay. Is that clear?
Okay, sir.
Okay. And now let me give you one example. Maybe that will make your idea more clear. Filter design. Let me choose another lecture, filter design. And this is actually designed for other section or other classes. Let me give you some idea on this because this is very important to understand the group delay concept. Okay. So as I mentioned this, the group delay can be represented by this. Okay, so the group delay is nothing but minus d theta by d omega. So by which you can understand the group delay. Let me give you one example where the linear phase and non-linear phase will be represented. Let me ask you one question. When there is a linear phase response, then what about the group delay? Is that constant or non-linear?
Constant, sir.
Constant, because your phase response is linear. So that means the group delay is constant. When the phase response is non-linear, definitely the group delay is also non-linear. Okay, it might happen that there is a non-linearity like this. This can be this can be like this, this can be like this, and this can be like this or something like this. Okay, this can be like this way as well. So the non-linearity actually done by the IIR filter design. Okay, let's have an example. You have your xn is a signal like sine 0 to pi n plus sine 04 pi n plus sine 06 pi n. So you have a signal like this where you have three sinusoidal combinedly represent your xn. Now let's say you have a LTI system, you have an LTI system where this LTI system is a FIR system. So this is an FIR system. What does it mean? What about the phase delay then? Phase response, linear or non-linear? For FIR system, the phase response is linear.
Linear. Yes, sir.
Yeah, linear. The phase response is always linear. So if the phase response is linear, then what will happen? The group delay is what?
Constant, sir.
The group delay is constant, and let that the group delay is 300. Okay, the group delay is 300. Now if the group delay is 300, we can represent it like this, and this group delay is 300 for all the frequency component. What are the frequency component you have in xn? You have 0.2 pi, 0.4 pi, 0.6 pi. So for all the frequency, from 0 to pi, the group delay is what? Group delay is equals to 300 samples. 300 samples for very practical case. So let me zoom in. Now I'm just plotting the xn here. So I'm plotting the xn. So xn is separated. It can be added together, but it can be also separated, isn't it? So this is the time frame. In the time frame, first we have our x1n, then x2n, and x3n. It can be, okay. It doesn't mean that xn is a combination, means it will be overlap. It can be separated, okay. So for this example, we make it separated. And this first signal, that means xn, x1, let's say this is x1, x1n, start with 0th sample. And this is x2, it start with 100 number of sample. And this is x3, start with 200 number of sample. Now this signal is given to this LTI system where the group delay is 300 samples. Now what is the starting point of this x1 in the output? What is the starting point? How much delay it will take? How much?
300, sir.
300 samples. That's why it starts with 300. What about the higher frequency component x2? How much delay it needs?
Sir, 300 plus 100, 400.
300 plus 100. So 100 plus 300 could be the right answer. So 100
Yes,
is the starting point plus 300. How we know that the 300 will be the delay? Because in this group delay diagram, 0.4 pi makes 300 delay. And as we already mentioned that the group delay is 300 constant. So in both way, you can find that, okay, the group delay is 300. So that's why 100 plus 300 is 400. Similar to this higher frequency component 0.6, what is the delay? The delay would be again 300. So 200 plus 300 is equals to 500. So you'll find exactly the same signal back after how many samples delay you need to give to the output to get the original signal back.
300, sir.
300 samples. And that's why this is very easy to understand or implement in case of which kind of filter? In case of
FIR, sir.
FIR filter. Okay.
FIR filter.
Exactly. So always think that the FIR filter is the easy and straightforward, because you do not need any feedback. Number one, you do not need to think about the group delay, because the phase response is linear. The phase response is linear. So this is all about the FIR filter, where the phase response is linear and our group delay is constant. Now think about a non-linear phase response. For understanding, I just make it like this. For 0.2 pi, the phase response is the phase response represented by this LTI system, which refers to the group delay is equals to 300. Let's say the group delay is 300 for 0.2 pi frequency. For 0.4 pi, this is 200, and for 0.6 pi, this is for 100, and for other frequency, this is 0. What kind of system we are talking about? We are talking about IIR system. We are talking about the IIR system, where the phase response is non-linear. That's why the group delay is also there is a non-linearity, or you can say the group delay is not constant. Okay, that is not constant. We can say that this is non-linear. We can say that this is not constant. Okay. And now moving forward, this is the same signals we are talking about. This is in the frequency domain. Okay, representation. And now we have the same signal. It start with x1 start with 0, x2 start with 100, and x3 start with 200. So can you tell me where the x1 will start based on this diagram?
X1, sir, it will 300 delay.
It will start with 300 delay. So it will start with 0 plus 300. So this is the starting point of x1. Let me choose the black color. So this is the signal, x1. And the green one, the x2.
Sir, 200 delay. It's maybe it's 200 delay. 100 plus 200.
So then 300. So it will also
300.
also start with the same time. So this is 200. Now what about the third signal? This is 100 delay.
200 plus 100, 300 delay. It's same.
It will start with the same point. So now you can see that we have this signal. Is this the signal we are looking for in the output?
No, sir.
No. So there is a problem. So now if we want to find the original signal back, you need to wait for the lower frequency for 300 sample, for the medium frequency again 300 sample, and for the higher frequency again 300 sample. So you need to know everything about this, otherwise they will overlap each other and you are getting some other kind of signal, and which is nothing but noise. So there is a term is called the noise due to the phase distortion. So this is called the phase distortion. So due to this kind of phenomena, we have the phase distortion, and that is not permittable. Okay, that is not permittable for the signal. So that's why there is a problem in the IIR system. So that's why people are thinking about the FIR system, though in case of IIR system there are some advantage. What is the fundamental advantage of IIR system? What is the fundamental advantage of IIR system? Any advantage? No advantage of IIR system.
Sir, mone nahi sir.
By introducing the IIR system, you can introduce the pole location rather situating in the origin. So you can shift the pole location, and by changing the pole location, you can improve the quality. You can improve the quality of the filter. Yeah, you can improve the quality of the filter very easily. In case of FIR system, you need to introduce more order. You need to introduce more order to improve the system. However, in case of FIR system, IIR system, you can introduce the pole location. You can introduce the pole location and you can shift it, and by which you can introduce a good quality filter. Okay. So that is the fundamental advantage. So that means with a low order, you can implement that. You can implement a good filter. Okay. So I would like to represent this with another example with the group delay concept. Is a very interesting one. So this is a all-pass filter. Maybe we need to give one example of the all-pass filter afterwards. In the all-pass filter, they will pass everything. Okay, so just concentrate on the representation of this. So let's say this is an all-pass filter. For all-pass filter, this is your phase response. This is your phase response, and this phase response is non-linear. Of course, this is a non-linear phase response. So what is the group delay? We'll find this group delay. If we make a little bit, okay. Okay, so we found the group delay. You can find what is the group delay. So this is the group delay profile, and the group delay at this location is 300 sample. So this is a very nice example. Let's say this is your input, where this frequency here we have a sinusoidal signal with a modulated signal. The signal is modulated by pi by 2, omega 0 equals to pi by 2, and this signal is modulated by pi by 8. So this location represent the pi by 2. This location represent the pi by 2. So the pi by 2 frequency is this. What is the delay of the pi by 2 signal? 300. So if I give it to the system, what kind of system? This system. Then pi by 2 will experience, this frequency will experience 300 delay. It start with 0, but at the output it actually start with 300. So that means it is actually shifted. It is shifted to 300. So from the 0, it is shifted to 300. What about pi by 8? So if this is pi by 2, pi by 8, let's say at this location, this is pi by 8. What is the shifting? What is the shifting it will experience? Pi by 8. How many samples? How many sample shifting it experience? Pi by 8? 0.
Sir, it is same as same.
Same. So that's why it starts with the same sampling position. So that means due to this kind of phenomena, group delay, the signals will be changes their positions, and this is a problem of the nonlinear phase response. Okay, I hope you understand the process. Okay, now if I ask you these two questions, FIR system, what is the advantage of FIR system? What is the advantage of FIR system?
স্যার এফআইআর সিস্টেমে পোল লোকেশন
From the phase delay, group delay point of view,
এটা স্যার গ্রুপ ডিলেটা হচ্ছে কনস্ট্যান্ট স্যার
for the FIR system, and for the IIR system, that is not constant.
নন লিনিয়ার হ্যাঁ জি স্যার
If you talk about the phase response, then FIR system has linear phase and IIR system has non-linear phase. From the group delay is constant for FIR system, and the group delay for IIR system is not constant. It will vary. It will vary, and that is a problem. Okay. So okay, so for designing the FIR system, there are few methods. Fourier series method without using the window function, Fourier transform method without using window function, and using window function. Apart from this, we also have another special method, the Kaiser. There's a known name, but this Kaiser is not that our Kaiser sir. So Kaiser empirical formula, also the Kaiser method is also very well known and well established method to design the FIR filter. So we'll go one by one, and they are not very difficult to understand, very similar to that one another. So design of low pass filter using Fourier series method. I'll talk about the steps, and you can go through the examples, and you'll find it very easy. So in case of Fourier series method, we start with this equation where the H omega will be given, H omega. So what is H omega? That is the transfer function, what we are looking for. So by definition, H omega should be given, and based on the H omega for the low pass, high pass, or band pass, whatever the case. So for H omega, from H omega, you will design your HN. That is our fundamental target. When we can design our HN, then we can implement our circuit as well. So in case of IIR filter, if we can remember, in case of IIR filter, we can design first the low pass filter, and after having our low pass filter, you can transform all other kind of filter. In the last class, you can design high pass filter, you can design band pass filter, because there is a transformation rule, band pass filter and band stop filter. All kind of filter you can design from the low pass filter. However, in case of FIR type, you can't do it. You need to do it one by one. You need to implement that for individually for the low pass filter, high pass filter, band pass filter, and band stop filter. So that is also a fundamental difference between FIR and IIR filter. Okay, so here by definition, what is the order of the filter and how we can implement those things, we'll talk about with an example that will give us clear idea. Without using window function. So design the low pass FIR filter without using window function. First of all, we are not using window function. How it looks like. Design a low pass FIR filter for the following specification. The cutoff frequency is given, the sampling frequency is given, the order is given. The order, N is the order of the filter, and the length of the filter is always order of the filter plus 1. So this is the length of the filter. Step number one, normalization of the cutoff frequency. As in case of IIR filter, we normalize the cutoff frequency as, so we know that how to normalize the cutoff frequency divided by FS, because sampling frequency is given. So we found the cutoff frequency is equals to this. Now fix the transfer function to be used. What is the transfer function? So this is the transfer function. They are making the transfer function is h omega is equals to 1 from minus pi by 2 to plus pi by 2. So what is our range of view? Our range of view is equals to from minus pi to plus pi. So that is, and our filter is equals to like this. So this is a low pass filter, sharp cutoff. This is pi by 2. And for the negative half, this is minus pi by 2. And this is 0. And this axis represent the magnitude response. So h omega. So for this value, the amplitude is equals to 1. And for this value, the amplitude is equals to 0. And this axis is omega axis. So this here, this is 0. So this is represented, this graph is represented by this equation or this mathematical term. So h omega is equals to 1 for minus pi by 2 to plus pi by 2, and elsewhere it is 0. Elsewhere that is 0. Okay. Now here in this case we do not care about the phase. If we care about the phase, then we can write it e to the power minus omega 0 n, where the magnitude is always 1. Here e to the power minus j omega 0 n, the magnitude is equals to 1. So that's why no need to put 1 there. So the same thing here, we consider the value omega. So at this moment we are neglecting the value of the phase. We are just considering the magnitude. So this is our filter definition. Here we are not using any window. So what about the window? We'll talk about this. So there is a sharp change. There is a sharp change. And let me clear the idea. When there is a sharp change in the filter, there is a problem in the time domain sequences. In the time domain sequences, we found that there is a jump or fluctuation. And this phenomena is known as Gibbs phenomena. So in this book as well, they talk about the Gibbs phenomena. So this kind of phenomena can be tackled by putting some window. So in future, we'll see that this sharp change can be changed with some window factor. So this sharp change can be changed with some window value, by which you can protect the sharp changes of this filter. You got my point?
Yes, sir.
Yeah. So in the case when we are not using any window, like this, we are not using any window, that makes a problem. What is the problem? There is a sharp change from 1 to 0, and that makes a huge jump in the time domain representation. That means there is a problem in Hn. So there is a problem in Hn, and which makes that there is a problem not in Hn, there is a problem in representation in the filter. In the filter domain, there is a problem, and that filter makes the things in such a way. Let's give an example. The frequency domain representation, when we are talking about a low pass filter, let's say this is your low pass filter, but due to this sharp change, it might happen that there is a huge jump, noise peaking jump, and then it will certainly make some kind of thing. So this kind of phenomena makes a lot of problem, and noise peaking, as well as there might be high amount of voltage in the circuit, which makes your system unstable. That makes your system unstable in such a way that it can be, the circuit maybe even burned. So that's why this is very important fact to consider a window. In the next section, we'll talk about the window. So before that, we just talk about the fundamental things without using the window. So this is the second step. First step is to find the omega c. Second step, to define our magnitude response or the transfer function. So fixing the transfer function. Now determine the impulse response. So we'll determine the impulse response by using the Fourier equation. So by using this Fourier series equation, we can do that. So do this expression. So this is easy in a sense. So we'll do the integration. So what is h omega? H omega is e to the power minus j omega 0 n. So do the integration for the value from minus pi by 2 to plus pi by 2. At the end, we'll find this equation. So this is a sinc function. So that is sine. So we can concentrate on this equation. This is enough. Sine n pi by 2 divided by n pi by 2 multiplied with half. So this is the sinc function we found. And now we determine the coefficient of the impulse response. Coefficient means Hn will be represented by H0, H1, H2, H3. So those coefficient we need to find. So the sinc function looks like this. If you represent the sinc function, it looks like this. And it will goes for infinite series. So it will goes to the infinite series. However, for FIR system, the window function, we need to cut somewhere else. We need to cut. Otherwise, practically, it will not be implemented. What is the order of the filter? For our case, this example, the order of the filter n is equals to 10. The length of the, then the length is equals to 10 plus 1. So 11. So that means in the right side, we'll take 5 samples. In the left side, we'll take 5 samples. And in the 0th position, we have a sample. So that means altogether, we need to take total, the length of the filter is equals to 11. So that is our concept. So we'll take samples. There is not, so how many samples we'll take? We'll take 5 samples, not more than 5. And then we'll shut down. In the next and the left side, we'll take also 5 and then shut down. And fortunately, they are symmetrical, isn't it? They are symmetrical. Since they are symmetrical, if I get the value in the right side, automatically you also get the value in the left side. So this is very simple in that sense. So let's start. H0. So if I put 0, then sine 0 by 0 is infinite. That's why we need to follow the L'Hopital's rule, where if the theta is very small, sine theta can be represented as theta. Sine theta can be represented as theta. In that case, n pi by 2 divided by n pi by 2. So that will give you, what is the value n? N equals to 0. That's why theta very close to 0 is equals to theta. So we are having theta is equals to pi by 2 divided by pi by 2. And now then we can find that is equals to theta is equals to 0. For theta is equals to 0. Theta equals to 0 means very sine theta is equals to 0. That's why the sine theta is equals to theta. So they will cancel each other. We are getting the value is equals to half. We are getting the value is equals to half. Basically, the value is 1 and multiplied with half is equals to half. So at theta is equals to, at n equals to 0, we got H0 is equals to 0.5. Similarly, if we do the calculation, now for n equals to 1, we'll follow the same formula. Now, we are not following the L'Hopital's rule because we have theta value now. For n equals to 1, we got this. For n equals to 2, for n equals to 3, for n equals to 4, and n equals to 5. That's it. Do you need to calculate n is equals to 6? No, because the total number of the length of the filter is equals to 11. So here we have 5, and where are the other 5? H minus 5, H minus 4, H minus 3, H minus 2, and H minus 1. Could you mention H minus 1 minus 5 equals to which one in the right side?
So minus.
Sorry, H minus 5 is equals to H what in the right
Minus
side?
H5.
H5.
H5. H5 is equals to H minus 5. Isn't it?
Yes, sir.
In the sinc function, what I mentioned, so let's say this one, and in the left side, this one. So here, let's say this is H5. Let's say this is H5. This is exactly the same as H minus 5. minus 5. They are symmetrical. So that's why we do not need to find those value again. Okay. So if we found h5, that means we also find h minus 5 with that value. So now this is your time domain representation. Hn is equals to this. And have you found any problem here? The problem is we have some negative sample position that shows that this is a non-causal system. But for implementation, we always want a causal system. We want a causal system. Okay, we'll solve that problem. So if this is our Hn, from the Hn, determine the transfer function block for the impulse response sequence. Determine the transfer function back from the impulse response. So how we can represent in the Z domain, we can represent it. So if you have Hn, very easily you can write what is Hz or in the Z domain. Now there is a problem. So this is the 0th sample. So this is the 0th sample, half. This is negative, this is positive. Now it makes a problem. This is a non-causal system. If we want to make it a causal system, what we can do, we can multiply the whole system. We can multiply the whole system with z to the power minus 5. So if we multiply the whole system with z to the power minus 5, then the system represent like this, and which represent that the total system is a causal system. And this is the output or the design value of your FIR system. That is the final output of the FIR system. And now you can implement this FIR system, and it is very easy. Definitely Xn having delay. So there is no delay. 1 by there is 1 by pi by 5. The 10 delays. 1 by pi. 1 by so for 2 delays, after 2 delay. Okay, so here we have multiplications of, can you see Xn, then there is a multiplier. What is the multiplier? Xn will be multiplied with 1 by pi 1 divided by 5 pi. So which equation you should follow to implement this? Which equation? This is the equation you need to follow. Okay. So here we have the delay positions are implemented. We have the delay positions. What is the delay there? If I count that this is a 0 delay, then this is a first delay, second delay, third, fourth, fifth, sixth, seventh, 8, 9, and 10 delay. So what are the delays? You should calculate it. This should be the reference delay 0, then first delay, second delay. So if you consider this equation, keep it in your mind, then what is the multiplying factor with the first one? The Xn is multiplied with 1 divided by 5 pi. After that, there will be 2 delay, and then it will be multiplied with what? Why there is a 2 delay? Because there is a 0, and then 1 delay, 2 delay. 2 delay is multiplied by minus 1 by 3 by pi. So this is very easy stuff. You can follow this one, or you can follow the upper sequences to represent your FIR filter. And you are designing your first FIR low pass filter, and that's it. So these are the steps. Okay. Adding more filter coefficient. Okay. The step number 7. So what is the filter coefficient? In the upper case, the filter coefficient is equals to actually from H0 to H10. That is the length. That means the length is equals to 11. So H0 to H10, that is the filter coefficient. If you want to increase the quality of the filter or the stiffness of the filter, if you want to increase the stiffness of the filter, then what you can do, you can add more coefficient. That means you can increase your value, let's say up to H20. or H40, you can improve the quality of the filter. But what is the problem? If I improve the coefficient, what is the problem? Looking for your answer. What is the problem?
স্যার অর্ডার চেঞ্জ হয়ে যেতে পারে নাকি?
Of course, the order will increase. And then what is the physical problem you faced? Is there any problem or issue? Your quality will improve, certainly. The problem is the computation. Definitely, when the order will improve, then the computation, that means you need the convolution. Always the system needs to do the convolutions with your input. So what you are doing, your system, this is your system. System has, previously you have 11 components. You do the convolution sum with your xn, and maybe you need some sort of mathematical calculation, and there are a lot of multiplication and addition. If you improve the order of the filter or improve the coefficient number, adding some coefficient number, then the multiplications, addition will also improve or increase. The actual number of the coefficient to be computed depends on the accuracy we need in the realization of the filter, as well as on the number of bits the computer used can handle. If you increase the coefficient, in some point of time, it may happen that your computer is not workable. It can't work with your coefficient values. It certainly improves the quality, but it will face some challenges from the computational point of view. Is that clear?
Yes, sir.
Yes, sir.
Okay. So if you understand this process, the process, step number 1, if I want to just repeat the things, very easy in a sense. First of all, definitions are given. First of all, you need to find omega c, step number 1. Step number 2 is you need to define your filter transfer function by using the equation for inverse Fourier transform equation. You need to find Hn in the time domain. From the Hn, you need to equation, and then we need to define the coefficient. After having the coefficient, you need to determine the z domain transformation or z transformation. If that is a non-causal system, try to make it a causal system and then implement it to the circuit, and that's it. If you are satisfied, always filter design is a trial and error method. If you are satisfied with this quality of the filter, you do not need to improve or add some filter coefficient, number 1. If you are more than happy with the filter design, then you can truncate it. You can truncate some of the coefficient as well. So let's say for our example, the highest coefficient or order is equals to 10. For order equals to 10, you are more than happy. Then I would prefer that, okay, go for n is equals to 8. And let's see how the filter works. If you are happy with this, stick with that. If you are again more than happy with this, then go for n is equals to 6. If you are happy with that, okay, stick with that. You got my point?
Yes, sir.
Yeah, because you do not know which order will actually make you happy with the purpose. It might with n equals to 10, or you need to improve that. This is always a trial and error method. And if you improve this one, maybe it is up to the mark, or even you are decreasing the thing, still it is up to the mark for your purpose. You know that what is your purpose. Okay. Now design of FIR filter using window function. Now we'll take the window function. Okay, so here to prevent the occurrence, so here I just stated that as stated above, finite resistor length, that means a finite coefficient of computer necessitate abrupt termination of FIR filter coefficients at some finite value of n. So we are abruptly we need to stop our coefficient, and there is a problem. In turn, this gives rise to Gibbs phenomena. There's a Gibbs phenomena. That means I already mentioned what is a Gibbs phenomena, which is dangerous in many situations, as it gives rise to sharp transients. So sharp transients can happen. So it might happen, there is a sharp transients like this. So there is a huge voltage surge. It might, in many situations, these transients may destroy the hardware used for the construction of the filter. So it must be avoided at all cost. So we need to avoid this one. So what we have already done with an example, that is not permittable. Always we need to consider the window factor. To prevent the occurrence of the Gibbs phenomenon, we must avoid the abrupt truncation of filter coefficient. The way to avoid abrupt truncation is to use a tapering characteristics. So this is the tapering characteristics. Okay, so you need to smoothly done these things. So this tapering characteristics actually been implemented not in the frequency domain, it is in the time domain. That means our coefficient should be tapering. Our coefficient should be gives this kind of shadowing or under this window, not in the frequency domain. The frequency domain presentation should be remain the same. The definition remain the same for the low pass. If this is a high pass, so the definition of the filter or the filter transfer function remain the same in the frequency domain, but we will implement this tapering or windowing characteristics in the time domain on the time domain coefficient. Let's say previously we have H0. Now, due to this truncation or the tapering characteristics, maybe we are multiplying with some factor alpha 0, so that we are getting a new coefficient H0 prime in the time domain. So that, let's say H10, previously what was the H10? Now we are making alpha, multiplying with alpha 10, a coefficient due to this tapering characteristic, so that our new H10 will not give the sharp change in the time domain. And that's why there is no kind of no Gibbs phenomena we will find in the transition of the filter design. Okay, so this kind of window can be implemented, and afterwards they are mentioning that, so by this window factor in the time domain, if you can concentrate here, this is in the time domain, they will be multiplied with our time domain sequence to represent a new time domain sequences. Typical window function. So first of all, we are using a typical window function. So the typical window function is a rectangular window. So the rectangular window is nothing but this one, the same thing, rectangular window. So we have already discussed about this, and it will not help us. It will not help us. Okay, it will not help us. So that's why they actually give the same thing. They will actually give us the same thing. So it will not help us. So it will produce the Gibbs phenomena. Okay. Next, the starting window or important window is called Han or Hanning window. Probably you heard this name. It's called Hanning window. What is Hanning window? This is the definition of the Hanning window pattern. Okay, so 0.5 plus 0.5 cos twice pi n over capital N for the value of n by 2 to minus n by 2. Why this is n by 2 by minus n by 2? Can you relate with the previous example? Previously, what was the value of n? It was 10. So n by 2 is equals to 5. So minus 5
to 5.
Yeah, minus 5 to 5. That is our value of n. That's why we can write it like this. So by putting m equals to n by 2, we can write it like this, or just for the positive side, we can write it like this from 0 to n, where n is equals to where n is equals to 10. So from 0 to 10 means 11. So we can also write it like this. So this is the definition of the Hanning window. This is the definition of Hanning window. So how it looks like? It is a cos function multiplied with half, and half minus this one. So at n equals to 0, you'll find that cos 0 equals to 1, cos 0 equals to 1, 0.5 minus 0.5. So what is the value? 0. So at the 0 location, there is no impact to the coefficient. Let me give you this example. So for 0, that means what is 0 means what? N, small n is equals to 0. So that means it correlates with H0. So it will correlate with H0. Ultimately, we need it for H0. This value is H1. That means what I am mentioning, H new coefficient, H prime 0, that means new coefficient is nothing but H0 multiplied with W Han, HAN 0. So what is W0? W0 equals to, at this moment, is equals to 1. Controls. So what is the equation?
They're going to plus sign this.
There should be, there is a mistake here. So there should be plus. Previously they are mentioning plus. Yes. Okay. So this is plus. So that is 1. So if I multiplied with 1, that means it will remain the same. W1 is equals to this, W2 is equals to this, and so on and so forth. Okay. Now it is represented here. It is represented with graphical presentation. So this is the window function. This is the window function. Now this window, that means each and every point will be multiplied. This point multiplied with H0, this point multiplied with H1, and they will produce the new value. This point multiplied with H2, and after that they will produce the new value H prime 2, and that is our new coefficient due to the window function. And this is all the values are presenting here. At 0 location 1, at the first location 0.9045, second location 0.6545, and so on and so forth. And the lower row shows the cos signal, if that is a fundamental cos. So just to compare between the cos function, it looks like a cos function, but a different phenomena, because it is multiplied with 0.5 and then 0.5 subtracted to that value. Okay, so this is that window. Now this is known as which kind of window? This is Hanning window. Okay, there is another window is called Hamming window. This is called Hamming window. What is Hamming window? The same pattern, but they are using this phenomena. Okay, and again they are making some. Okay, so they are having this value and this value 0.5, 0.54 plus 0.46 cause this value, and they are defining this value like this. Okay, and of course, again, they are making some mistake. That should be plus. That should be plus, and this cosine window can be also known as raised cosine window, the Hanning window, the Hamming window, and the Hanning window shows the sharp fall. So here we have the sharp fall comparing to this window. So we have some Lenden window. So we can compare these two window. We can compare those two window afterwards. So if we want to compare these two window, what is the purpose of this two window? That is an important fact. So what is the difference, or what is the goal to understand this kind of window. So let me give you some example. This is the Hanning window pattern, the red one, and this is the Hamming window pattern. Okay, so this is Hanning and this is Hamming. Practically, how they looks like, if you want to plot it. So if you know, this is in the time domain or in the frequency domain.
Frequency domain.
In the frequency domain. So the magnitude response, if I know the magnitude response of this kind of filter or this kind of window, that means the Hanning window, in the same plotting, you will find this kind of phenomena. So the green one, the blue one, let me zoom it out. The blue one is the Hanning and the red one is the Hamming. Try to concentrate here. There are some advantage of Hanning window and there are some advantage of Hamming window. What is the advantage of Hanning window, first of all? By seeing this figure, can you let me know what is the advantage of Hanning window?
ম্যাগনিটিউড যেটা আছে সেটা হলো হ্যানিং উইন্ডোর জন্য মানে আদার ইকুয়াল অ্যামপ্লিটিউডটা কম,
other frequency. So for the stop band, you have very low gain for the stop band and sharp fall. And the sharp fall. Let's say this is your pass band 0 0. This is in the dB. 0 dB means 1. Okay, 0 dB 1. So this is your basically pass band. So here we are passing the signal. And where is the stop band? If this is a minus 20 dB per decay system or something like this, so after 20 dB, let me give you this. After 20 dB, you'll have very low gain, and this is very good, isn't it, for the Hanning window? Are you with me?
Yes, sir.
Okay, so
Yes, sir.
this is very low, so that's why this is the advantage. But one disadvantage you will find that in this case we have a higher value in case of Hanning window. This will take very high amount of signal of the high amount of signal from the noise. It might take high value of the noise. You got my point?
Yes, sir.
Okay. So that is a problem. Advantage is definitely the higher frequency will goes down and we don't have any tension over that. But what about so let's say this is your actual frequency band, the 0 hertz, and you want to pass it up to this. But they are, these frequency components are making some kind of chasing. That means they are the competitor of your original signal, and they have a very high gain. Still, they have a very high gain, and that makes a problem of the Hanning window. But what about the Hamming window? Hamming window is in other case, after the pass band, in case of stop band, maybe there are some amplification gain, but they are very small. But what about the competitors? So your competitors are nullifying. If you can see there, can you see there? Your competitors are there, and they are, with comparing to the Hanning window, Hanning window, they are much lower than the Hanning window. You got my point?
Yes, sir.
Yeah.
Yes, sir.
So that is the comparison between Hanning and Hamming window. Okay, so interesting. Similar to that, we have other kind of window. We'll talk about this and the comparison as well. Now let's do some example with this Hanning window. So let's with the same example. So in the previous case, we done this. Can you remember for the low pass filter? For the low pass filter, we found the Hn is equals to this. How we can find this? First of all, we defined omega c, then we defined h omega. From there, we define hn. Is that clear?
Yes, sir.
So hn is equals to g. That is a sinc function, half of the sinc function. So up to this we have done. So now we will implement the Hamming window with this signal. So do the same thing. So this is for the Hamming window. So we know this value, and we need to find h prime 0. We already found h0. Then multiplied with the window factor, and then we found the final value. Similarly, what is h prime 1 is equals to h prime minus 1, because they are symmetry. This is the value we found. This is h1. This is the value from the window factor, and this is the final value. So a little bit change. So if you can compare these two, there is a little bit change of this one. h3, this is the h3 multiplied with window factor, and there is a little bit change or huge change. There is a huge change you'll find in the factor. Similarly, this is h5 multiplied with window factor, and there is a small change or huge change. There is a huge change because the multiply factor is 0.08. So you found a huge change in the output. So whenever we found h prime 1, h prime 2 is h prime 3, h prime 4, and h prime 5. That's it, because we got the negative sample result instantly. And we follow the same formula, and we have this. And this is our final result. This is our final. So here we have z to the power 5 showing the non-causal system. We want to make the power is equals to 0 at the very beginning by multiplying z to the power minus 5. And then we have this non-causal, the causal system. So this is our final result. Solution using the Hanning window, Han window or Hanning window, the same thing, just the window factor will change. There is another generalized Hamming window. There is a name is generalized Hamming window. What is that? Some other scientist, Rabiner and Gold, in 1975, they combinedly represent the Hamming window and Hanning window together, and that is known as generalized Hamming window. Okay, so they are representing alpha and the value of m. So where they are representing value of alpha and the value of m. So where alpha, you can change the value of alpha. For Hanning window, alpha is 0.5. For Hamming window, alpha is equals to 0.54. Now you have the ability to change the value of alpha for trial and error. Okay, so what is the idea? Idea is that you are implementing a window. Now you are not satisfied with the result. Now you need to modulate the window pattern. So you can do it. You can change the value of alpha so that you can increase the value or decrease the value, so that you are very close to your desired filter. Like this. If I have Hanning window to Hamming window, if I want to go in between these two, how we can change it? By changing the value of what? How I can change the Hamming window to Hanning window?
Changing alpha.
Changing the value of alpha. So that is the advantage over that equation. So we can modulate. So there is a window, is called the Bartlett window. This is a triangular window. There is a Kaiser window, and there are different sort of window. Just to give an idea of different sort of window. Okay, this is the example where we can find, this is for window transfer function, conventional one. This is the Hanning window, and this is the Hamming window. So this is a conventional, means what? A window like this, square, sharp window transformer, window length is 20. So like this, what is the, how it looks like. So this is your signal amplitude 0. 0 is the maximum, and minus 20 dB per decay is this one. So how it looks like. And here this is a minus 20 dB per decay. So this is very good one. Minus, maybe your signal is like there, or your signal is like there. Still, how their looks like. So I would prefer Hamming window over Hanning window, because this is a problem. This first lobe is a problem. This can take your competitor. But here, if I go for this, there is no competitor will come. Though there is a, they have some magnitude response in the higher frequency, but they are very small in a number. So then we can neglect those. Okay, so these are the different pattern. Hamming and Hanning, they are looks the same. This is the Bartlett window. This is the Kalman window. They looks almost the same, but you know that there are some bit of change. There is a very sharp high and flat low, and there is a Kaiser window. We'll talk about more about the Kaiser window at the later part of the lecture. And these are the comparison. Okay, so I already mentioned the basic things. Now you can compare between these filters, which one you prefer for your purpose. Okay, so you can compare the filters by their filter responses in the frequency domain. So I believe that you can go through this yourself, and then you can understand. And afterwards we'll talk about the Kaiser filter when we go to the next section of this chapter. So they are making the comparison between the function. They are making the comparison between the functions here. I already gives you some idea of the comparison. So you can go through this and you'll find it very easy. Are you comfortable with the lecture?
Yes, sir.
Yes, sir.
Okay. So if you can concentrate, I need more time to explain the things. Okay. Are you okay with this?
Yes, sir.
Okay. Now design using the frequency sampling Fourier transform method. So now previously we'll use directly HN, and we found the value by inverse Fourier transform, and then we'll go for H0, H1, H2, H3. Now what we do, we'll do the same thing, but what we are doing the DFT concept. So that means previously the frequency domain representation was a continuous one, and now it will be discretized. So previously it was a continuous one, now it will be discretized. That is the fundamental difference. Okay, nothing else. So very easy. So now, and afterwards the samples are 0. So up to this, let's say this is pi by 2, and this is up to pi. And in that case, of course, there is a minus pi, and that will be replicated in the left side as well. So this is the fundamental difference. So there is nothing new here. Okay, so you need to be very relaxed on the lecture time. So nothing to mention here. This is an inverse DFT. Every part should be known to you. And in case of DFT, we represent our signal with a value of k, because they are sample. Previously, we represent H omega, because omega is a continuous one. Now, this omega, the twice pi, is divided by number of samples. Here, the number of sample is n plus 1, the length. So the whole spectrum, let's say the whole spectrum. So in DFT, if you can remember, 0 to pi, and there is a minus pi, we shifted it to the positive side, and we actually take from 0 to twice pi. That is our whole spectrum. And the whole spectrum is divided. Whole spectrum is divided with the number of samples. So what is the whole spectrum? This is twice pi. And what is the number of samples? We are spreading that, spreading from 0 to twice pi. This is n plus 1. So we know what is the frequency hopping. So what is the frequency hopping? The frequency hopping is twice pi divided by n plus 1. What is the number of samples we have? Okay, so that is the fundamental difference in the continuous time and the discrete domain. Now we can move to the example that will give you some idea very easily. So this is the whole spectrum, where for the low pass filter, we will consider this portion, only this portion, and that is magnified here. So let's say 0 to pi by 2. Pi by 2 is your cutoff. Then this is the pi. Pi means this. What is this? Omega s. Pi means actually our sampling frequency. Pi means the sampling frequency. Are you agree with me? Pi means sampling frequency.
Pi. Yes,
F by
Yes, sir.
Fs. F by Fs is your omega. So at the location of pi, what is the value of omega at the at the location of pi? What is the value of small f? Can you recall? It was half. That means at this location, this f is twice of at this location, the f is half of fs. So that means this is equals to half of fs. Half of fs. Capital Fs. Otherwise, the sampling frequency, the Nyquist theorem, will not hold. Okay. So in that case, the value of f, small f, is equals to this. So omega equals to what? Omega is equals to twice pi small f. What is a small f? Is half. So that means the omega is equals to pi at that location. It shows that it represents the
Yes, sir.
sampling frequency. It represents a sampling frequency is omega s. Okay. Okay. And this is 3 pi by 2 accordingly, and this is twice pi. So this is our full spectrum now. This is our full spectrum. Our range of view is from 0 to twice pi. Because we are doing what? We are doing the DFT. Because we are doing DFT. They are talking about the Nyquist theorem and other things. So I have already given that example. Okay. Now with an example. The cutoff frequency is 500 Hertz and the sampling frequency is 2 kilohertz. N is given and the length is also given. Okay, nice. So what is the first step? The first step, the steps are the similar one. Okay. The first step is to find omega c, that is cutoff. We found pi by 2. Define the transfer function. So of course, the transfer function, according to the transfer function, it will remain 1 for 0 to pi by 2, and from 3 pi by 2 to 3 pi by 2 to other value. So they are representing the same. From 0 to pi by 2, this is 1, and from pi by 2 to pi, it will be 0. And then it will be replicated. It will be replicated. So that's why, first of all, we are concentrating up to pi, and that will be common for the other portion. Okay, so our range of view is this, of course, but first of all, we'll calculate for this. And since we know that they are symmetry in the pattern, then if we found this value, we can easily say that this is also true for this value. If we found this value, we can easily say that, okay, this is also true for this value. So that's why we are just concentrating on this part, first of all, and then we'll move to the right side. Okay, continuing with the example. Determination of the location and the amplitude of the sample. So we need to determine the location and the amplitude of the sample. So that means now we have the samples, where the samples positions are. So all the locations we are not getting the sample position, because what is the resolution of the frequency? The resolution of the frequency is equals to twice pi divided by n plus 1 because we have n plus 1 number of samples. So that is the resolution of the two sample. So let's say we have a sample there, we'll find there. What is the next sample location? And that is the delta. And we know that. What is delta? What is the other samples? So if you are fortunate, let's say you are getting this, maybe the other sample, 1, 2, 3, 4, fifth sample will goes there. It might happen. So similarly, you will get 1, 2, 3, and 4, and fifth sample will go there. The symmetry, we'll get the symmetry. So now our target is to find this amplitude and the position. First of all, the position. If you found the position, you can find the amplitude, isn't it? Which one you need to find first, position or amplitude? You already defined your amplitude. Now what is next? You need to find your what? Amplitude or position?
Positions.
Position. If you find the position, if you find that, okay, this is the 0th sample, you can find what is the position. If you find this is the first sample, what is the position? This is the third sample, what is the position? This is the fourth sample, what is the position? 0. What is the fourth sample? You know the position, then you know what is the amplitude very easily. Okay, so that is the task we will try to do. So we are trying to find the positions, and this is the diagram by which we just show that, okay, what are the position for k0 is 0, k1 what is the position, k2 what is the position, and so on and so forth. We'll find all the position. We know this value is pi by 2, already know what is the value. So what are the positions you can find based on that position? So we are finding for k1 is equals to 0.57, k2 1.14, k3 is 1.7, k4, k5, k6. So we need to find up to 11. And 11th sample, if you talk about this, it belongs to twice pi. It belongs to twice pi. So that means it belongs to the next cycle. Because by this time, we already have 11 sample. Because k starts from where? K starts from 0. 0, 1, 2, 3, up to 10 means you have 11 sample already. This 12th sample belongs to the next cycle. If we have the samples like this is 0th sample, and this is 12th sample at the location of twice pi, and this is pi. So this 12 pi belongs to the next cycle. We do not bother about this. We just calculate this just to show that we are at the location of twice pi, isn't it? 2 pi. 2 pi means at the location, 2 pi means 2 into 3.14 is equals to 6.28. Just to show that, okay, at the 11th sample, we are finding the twice pi location, but it belongs to the next cycle. Now it is represent, okay, the 0th location, definitely 0, the first location position with scale of omega, with the scale of omega, definitely multiplied with pi. So they are already multiplied with the pi value, and this is the value of omega. It represents the value of the omega. So you found the positions. Now from there, can you find the value? Yes, of course, we found the value. And from there, we can find that H3, if I go back to there, the H2, the second location, try to find that. The second location, what is the value? 1.14. 1.14. Here. The second location is 1.14. What is the boundary for pi by 2? 1.57. After 1.57, everything is 0. After 1.57, everything is 0. So where is 1. So after this, we have 1.7. So that means H3, what is the value should be H3? What is the value of H3?
0.
0. Because it is after pi by 2. Very good answer. So after that, it will gives you 0. So that is, they are mentioning H0, H1 and H2. In the left side is equals to your H9 and H10. H11 belongs to the next cycle. So forget about this. So we have H0, H1, H2 and H9 is equals to 1. From the diagram, you can find it. From this diagram, you can find it very easily. And it is described here. So this is 0, this is for 1, this is for 2, the value is given, and this is the third sample. Third sample is out of pi by 2, that's why it's 0. This is 0, this is 0, this is 0, this is 0, and this is also 0. And this is the 1, and this is 1. So this is H9, H8, and H9. H10 belongs to the next cycle. This is H0, and this is H1, and this is H2. The H1, H0, 1, 2 is equals to H8, H9, what we mentioned. And H3, H4, H5, H6, H7, and H8, sorry, this is 9, and this is 10. Yeah, 9 sample and 10 sample. H11 belongs to the next cycle. So they are 0, 3, 4, up to 8, they are 0. Now you already determined all the value of Hn by using this equation. So we already defined capital, that means in the frequency domain, this is our fundamental equation where we already define H0, H1 to up to H10. So do the inverse Fourier transform. Do the inverse Fourier transform, and you can find the equation. This is the equation where you need to, this is the equation. Here you need to put the value of n is equals to 0, n equals to 1, 2, 3, so on and so forth. And interestingly, you need to, if you can put all those data, and you'll find that again, the H0 is equals to H11, H1 equals to H10, H2 is equals to H9. So they will come in a couple. They will have the replica, and this is the fundamental equation for your filter design in the Z domain. If you find Hn, of course, this is very easy to find Hz, and then you can implement that. Is this process clear to you?
Yes, sir.
Yes.
Yes, sir.
Okay, this is easy, straightforward. Now using window in the design employing frequency sampling method. So we are using the same thing. Now we are using the window. We have done the thing what we have done in the last section without the window. We are finding this coefficient without the window. Now we are implementing the window, what we have done before. Just now we are multiplying the window factor. Let's say W hand 0. So you are multiplying, and now you are getting H0 prime. The concept is like this. And now you can do the same thing for a whole bunch of data, and you are getting H1 prime, H2 prime, something like this. And now definitely the filter quality will improve with the windowing the time domain responses, and they are doing the same thing. Okay, so you can follow the process, nothing new, just window function. Window function is incorporated. Window function is incorporated with your previously defined time domain transfer function, time domain impulse responses. Okay. Okay. Now design of FIR filter using frequency sampling method when characteristic is practical and not ideal. What does it mean? Previously, we'll give a sharp change like this, sharp change. Now it is defined as the practical change. So it might be like this. Okay, so this is the change now. Previously it was a sharp change, what we have done. Now practical cases, we are not permitting the sharp change, we are giving a smooth change like this. Is that clear to you?
Yes, sir.
Okay. So the idea is plain and simple. You need to define your filter first. with those points like omega 1 and what is the value of omega 2 that should be given. And from there you can find omega c. How you can find the omega c? Just add those together divided by 2. So just give the average of this omega 1 and omega 2. So I'm just declaring the idea, or make it the idea clear first of all. So then when you are defining your filter, you need to define in this way. So the second step is, first step is what? You need to define the value of omega 1, omega 2, and from there you will define omega c. And omega c is nothing but omega 1 plus omega 2 divided by 2. So that is how you define everything. And now the thing is, what is this amplitude? This amplitude is 1. You know this amplitude. Now the second step is you need to define the position, isn't it? You need to define those positions. What are the positions for different value of k? Now, in some point, it will be merged with this line. So what is the amplitude? You need to also define those amplitude as well. So first define the position, then define the amplitude. Those amplitudes are nothing but what? If I mention it here, this point is what? H0. This point H1, H2, H3. This is H4. Let's say this is H4. How you can find the value H4? By doing some trigonometry, you can find what is the value of H4 if you know this value. If you know this value, if you know this point and this point, definitely you can find what is this value. Can you find this?
Yes, sir.
Of course, you should find this. If you know this value, that means the amplitude and the position. If you know this value, what is your purpose? If you know this value as well and know this value, now you need to find this value. Okay, so I believe you can find it, and the formula is also given here, but logically you can find this value. So these are the steps. Step number 1, finding those values. Step number 2, finding the position. Step number 3, finding those amplitude h. If you find this h value, then what else? Then you need to find what? Hn, isn't it? From H0 you'll find,
Yes, sir.
yeah, capital H0 to small h0, capital H1. So with a combination of this, you have the formula. You have the formula, inverse discrete Fourier transform. By using the formula, you need to find Hn. When you can find Hn, everything is done. If you try to implement the window, then you are allowing the window factor with that, and that's it. And that is the implementation of design of FIR filter using the frequency sampling method when the characteristics is partially and not ideal. Partially, or you can say not ideal. Okay, so step number 1 is given. This is omega 1, omega 2, and omega c. This is the definition. Okay, from 0 to omega 1, the amplitude is equals to 1. From omega to omega 2, this is 0 for 0.8. Okay, so that is by definition. So they are defining this value and defining this value. Okay. Then this is the resolution, twice pi divided by n plus 1. They are finding the position. They are finding the position, this position, what is the positions are there. After finding the position, they are finding the magnitude. Okay, so we need to find the magnitude of this location. This is not critical. You'll find the magnitude is 1. These 2 locations are critical. For these 2 position, what are the amplitude? What are the amplitude? They found those amplitude here. Okay, so follow this and you'll find it. So they have found all the values. They have found all the values. So there is a mistake. So this should be replaced by capital H. So this should be replaced by the capital H. So when they found the capital H, after having this equation, you will find small hn value. Okay, when you found the small hn value, then you will find the capital Hx value, that means Z transform value, and that's it for the design process. Is that clear up to this?
Yes, sir.
Yes, sir.
For the high pass filter, you need to follow this one. I will not go for this. Only difference is the definition. The definition is different. You will follow the same formula. Okay, so just go for that. For the band pass filter, only the definition is changes. Everything will follow it. Follow this previously what we have done. So nothing new here, just the integration part. Band pass filter, just the definition is different. Other than everything remain the same. Okay, so up to this we can finish, because there is a topic like the Kaiser filter approach. Probably that will take some time, and it's long time. We have already almost very close to 2 hours, so it might be difficult to handle from your side as well. So in the next class, we'll talk about the Kaiser approach from this, number one. Number two, I will talk about all pass filter, because I believe that you have some problem with group delay, phase delay, and why this is important for the filter design, because since we are talking about filter design, it should be understood. So that needs one class. And I would also like to give a small lecture on multi-rate signal processing. Multi-rate signal processing, just the introductory idea. What is multi-rate signal processing, and what is the implementation? Just a short note, okay? So if we can conclude that in the next class, that is the end. If we can conclude that, then maybe a half an hour or 1 hour classes we might need it. Okay, so the next class will be on the next Friday. Okay.
Okay, sir.
On the next Friday, and then we'll decide whether we need another class to end up the syllabus. So thank you for your time and participation.